All right, let's pull back the curtain on one of the coolest, most important ideas in modern software, event-based concurrency. You might not have heard of it by name, but it's the secret engine that's powering some of the fastest, most responsive apps you use every single day. Let's get into it.
So, have you ever stopped to think about how something like a Node.js server or Nginx can handle like thousands of people all hitting it at the same time without even breaking a sweat? It seems almost impossible, right? Well, it's not magic. It's actually a really clever and super efficient design. And by the end of this, you're going to understand exactly how they pull it off.
Okay, so before we can really appreciate just how brilliant the solution is, we first have to get our heads around the problem. And we can sum it all up with a simple idea I like to call the busy waiter problem.
Imagine you're a chef, and you've got 10,000 tiny pizzas in a giant oven. Your job is to grab each one the second it's perfectly cooked. Now, the bad way to do this is something called busy waiting. You'd literally just run back and forth, opening the oven door, checking pizza 1. Is it done? No. Pizza 2? No. All the way to pizza 10,000, and then you'd start all over again. You're always busy, but almost all of your work is just pointless checking. In the computer world, this burns through CPU cycles like you wouldn't believe.
And when you look at the numbers, the inefficiency is just staggering. Constantly asking, "Are you ready yet? Are you ready yet?" can waste over 99% of your processor's time on, well, nothing. The event-driven way, on the other hand, completely flips this on its head. Instead of asking, the system just waits to be told. It waits for a notification. The difference in efficiency here is, it's truly night and day. And yeah, this is what that grind looks like in practice. Your program is just stuck in this endless loop. Check connection 1. Got anything for me? Nope. Connection 2? Nope. Connection 3? All the way down the line. If the data you're waiting for finally shows up on that last connection, number 10,000, you've just wasted 9,999 checks for absolutely no reason. It's tedious, it's slow, and it just does not scale.
So how do we escape this trap? Well, it takes a totally different way of thinking. We have to stop constantly asking questions and instead start listening for answers. We have to start thinking in events.
And this right here is the big aha moment. What if, instead of you checking the oven, you just put a little timer on every single pizza? Then you could go chop vegetables, wash dishes, do other useful work, and when a timer goes off, ding, it notifies you that a pizza's ready. That ding, that notification, that's an event. The huge takeaway is that you are freed from the boring task of waiting. You can use your time for actual work until you're told you're needed. So let's nail this down. What exactly is an event? It's really just a notification that something important happened. It could be that data you're waiting for has finally arrived on the network. It could be a timer going off. Or, if you think about user interfaces like in React, it could be as simple as a user clicking a button. Each one of these is a signal to do something.
Okay, this is a great idea, but a concept isn't enough, right? How do we actually build a system around it? What are the moving parts that make up this whole event-driven engine?
Well, the first key component is called a callback. A callback is simply the chunk of code you want to run whenever your event happens. Think about it like leaving your phone number instead of waiting on hold. You're not just going to sit there listening to bad music. You're saying, hey, call me back when you're ready, and when you do, here's what we need to do. In code, it's the exact same idea. You're giving the system a function to run when that data finally arrives. Now, a quick reality check here. This style of programming is incredibly powerful, but it's not perfect. Sometimes you have an operation that finishes and triggers another, which then triggers another, and another. Pretty soon you can end up with this deeply nested, indented code that developers have let's say a loving name for: callback hell. It can make code kind of hard to read, but luckily modern languages have come up with clever ways to manage it.
So if events are the signals and callbacks are the instructions, who's the dispatcher? Well, that's the event loop. The event loop is the central controller, the conductor of this whole orchestra. It has one simple, never-ending job: check a list for new events, and when it finds one, it grabs it and runs the callback that goes with it. It's the tireless heart of the whole system, which is why people call it the heart and soul of runtimes like JavaScript.
So, when you put all these pieces together, the events, the callbacks, the event loop, what you get is a formal, reusable architecture. It's a famous software design pattern, and its official name is the reactor pattern.
And the cool thing is, we've already met most of the players here. The event sources, those are our pizza timers or our network connections. The event handlers, that's just a fancier name for our callbacks. The reactor, that's the event loop itself.
But that fourth piece, the synchronous event demultiplexer, whoa, that sounds complicated. But trust me, that's the secret sauce that makes the whole thing work so efficiently.
So what is that thing? Well, it's a feature built right into the operating system, with names you might have seen like Select or ePoll. Instead of our app doing the busy waiting, it just hands a whole list of connections over to the OS and says, hey, wake me up when anything happens on any of these. The operating system is amazing at this. It does all the waiting for us so our program can just sleep peacefully until the OS sends a notification that there's real work to do.
You know, really understanding this pattern helps us clarify two super fundamental concepts in programming: synchronous and asynchronous communication.
And the difference is actually beautifully simple. Synchronous is like a phone call. You say something, and then you have to stop and just wait for the other person to reply. You are blocked. Asynchronous, on the other hand, is like a text message. You send it, and then you're free to put your phone down and go do other things. The response will get there when it gets there, and you can deal with it then. You are not blocked.
So the huge advantage here is that this asynchronous model totally decouples the sender from the receiver. The sender can fire off a request and immediately move on to other work. And all those precious system resources, especially that CPU time, get used for actual work instead of just sitting around doing nothing. This is the real key to handling thousands of things at once. All of this brings us to these four main models for handling I/O. The reactor pattern we've been talking about fits right into this category called asynchronous blocking. Now, I know that sounds like a total contradiction, but it actually makes sense. The I/O operations themselves are asynchronous, but our program makes one single blocking call to the operating system that basically says, block me, put me to sleep until you have some news. It's the most efficient way to wait. So, there you have it. From the web server that sent you this content to the app running on your phone, the reactor pattern is one of the true silent engines of our digital world. Now that you know how it works, the real question is, where else can you spot this powerful idea at work? Thanks for joining me.